Hello friends. Today we will learn about flow of electricity. Let's go with the flow of electricity. First, look at how electricity is generated. Almost all electricity we use comes from generators, in which massive magnets surround equally massive coils of wire. Water from a dam, or steam created by a nuclear plant or fuel-burning plant, spins the wire coil rapidly, creating a high-voltage alternating current that is transmitted via thick, low-resistance cables to electrical substations throughout urban areas. This is the path of electromagnetic wave. This is how an atom looks like. This movement of electrons, which occurs only under the right circumstances, is electricity, and it travels at the same speed as light, another form of electromagnetism, 186,000 miles each second. Straight from the generators, electricity measures in the thousands of volts, much more powerful than we need for everyday uses. Even in the home, the voltage of current from a wall plug is many times more than most household electronics need or can tolerate. Within those same electronics, different components require still smaller and varying voltages and amperages, higher or lower than the current flowing through most of the circuitry. How, then, can we control all this? At a power station, steam generated from burning coal or heat from a nuclear plant turns a shaft within an electric dynamo. The shaft is attached to a rotor covered with thousands of wires called bushings. The rotor turns inside two permanent stator magnets whose fields generate high-voltage electricity in the bushings that is transmitted as alternating current on the public power grid to homes and businesses. At a power station, steam generated from burning coal or heat from a nuclear plant turns a shaft within an electric dynamo. The shaft is attached to a rotor covered with thousands of wires called bushings. The rotor turns inside two permanent stator magnets whose fields generate high-voltage electricity in the bushings that is transmitted as alternating current on the public power grid to homes and businesses. Before the electricity reaches its final destinations, it passes through a transformer to reduce the voltage. A transformer has a common magnetic core, usually iron, around which two wires are wrapped. Alternating current AC, electricity that flows first in one direction and then the other, moves through the primary coil, the wire that has more wrappings around the core. Each time the current switches directions, its magnetic field expands or collapses, which is the same as the field moving, and induces an electrical current in the coil. The current passes through the part of the core around which is wrapped the secondary coil. There the AC produces another magnetic field that envelops the wire wrapped around the core. The field creates a current in the secondary coil, but because the secondary has fewer wrappings, the current created in the second coil has a smaller voltage, making this a step-down transformer. A step-down transformer, which is most likely mounted on a utility pole near your home, cuts the voltage on the raw generator current from thousands of volts to 120 volts V before it's allowed inside. Before a computer can use the household current, the current passes through a second step-down transformer, this time in the PC's power supply, the box festooned with warnings not to open it that's at the back of the computer. This transformer reduces the 120 volts current into two different voltages that separate wires carry to 5-volt and 3-volt components. Other electronic devices, such as amplifiers, use a step-up transformer to raise the same 120 volts to a level powerful enough to drive speakers. We use resistors to decrease the flow of electricity, much like we use a valve to limit how much water flows through a pipe. Resistors are commonly made of carbon, plastic doped with metals, and metals such as nickel-chrome that do not conduct electricity well. Varying the materials and their size and shape changes how much resistance the component has, measured in ohms. Variable resistors, such as the rheostat shown here, are used in situations that call for the resistance to be changed manually, on the fly. The best example is the traditional dial controlling volume on a radio. The outer ring, or toroid coil, consists of a resistive wire wrapped in a spiral about a ring of insulating material. Electricity must travel along a sliding wiper and through the coil before it leaves the resistor. When the knob is turned clockwise, the electricity has less wire to travel through so that the resulting current is stronger and the volume is louder.